In other videos, we introduced ourselves to the idea of orbitals, and these are various orbitals in their various subshells that you could find in various shells of an atom. And in this video, we're going to get a little bit more practice with electron configuration. In particular, we're going to expose ourselves to the idea of the Aufbau principle. Now, Aufbau comes from German, means the building principle. It's a very useful way of thinking about electron configurations past calcium. Let's just get a little bit warmed up. What is the electron configuration of neon? Pause this video and think about it, and as a hint, I will give you the periodic table here. All right, well, neon has an atomic number of 10, and if we're talking about a neutral neon atom, it's going to have 10 electrons. And so the first two will fill that first shell. So we have 1s2, and then the next two are going to fill the 2s subshell in your second shell. So then you're going to have 2s2. And then we have 6 more electrons to get to 10. And that's now going to fill your 2p subshell. So 2p6. And so what's the order of the subshells that we just filled? Well, first we filled 1s. Then we filled 2s. Then we filled 2p. And you can also see that in the periodic table of elements. In this first row, you're filling that first shell. In this second row, or this second period, you are filling that second shell. Now, what's going to happen if we were to go to, say, argon? So if you're going to go to argon, what will that electron configuration look like? Pause the video and think about that. Well, we can use the noble gas configuration or the noble gas notation. We could say, all right, we're going to be building off of neon. So we're going to have the electron configuration of neon, but then we're going to add electrons into our third shell. So from neon, we would then add 2 electrons into the 3s subshell, 3s2. And then to get to 18 electrons, we're at 12 right now, we're going to have 6 more that are going to be in the 3p subshell. So 3p6. So on this diagram over here, we went from 2s to 2p to fill up neon. And then as we went to argon, we go to 3s to 3p. Now, what would be the electron configuration of calcium? Pause the video and think about it. All right, well, calcium has 20 protons, so a neutral calcium would have 20 electrons. So 2 more electrons than argon. So we can build off of argon. And where are those electrons going to go? And this is where the Aufbau principle is interesting. There is indeed a 3d subshell, but in the case of calcium, instead of those 2 electrons being in the 3d subshell, they end up in the 4s subshell. So calcium's electron configuration is the same as argon, and instead of it being 3d2 here on top of that, it goes straight to 4s2. And so that's why I was drawing this diagram like this, and you'll often see that in an introductory chemistry class. You fill 1s first, no surprises, you're filling in that first shell. Then you fill 2s, then you fill 2p, and you filled your second shell. Then you go to 3s, once again, no surprises. Then you go to 3p. Now this is the surprise and why this Aufbau diagram is useful. For electron configuration purposes, if you're thinking about potassium or calcium, the extra electrons are now going to go in the 4s subshell. So now let's think about what the electron configuration of scandium would be. Pause this video and think about that. Well, scandium has 1 more proton than calcium, has 21 protons, and if it is neutral, it's also going to have 1 more electron relative to a neutral calcium atom. And so it could have a similar electron configuration, so we could base it off of argon. We have 2 electrons in the 4s subshell, so I'll write 4s2, and the Aufbau principle would describe that. And the Aufbau principle, this little diagram would say, all right, that other electron is going to be in the 3d subshell. So you do 3d1. And this is indeed an accurate electron configuration for scandium. Now, the Aufbau principle makes you think that you're filling 4s first And then you are starting to fill 3D if you're actually building up a scandium atom. And that's actually taught in most chemistry books and in most classes. But actually, if people start with a scandium nucleus that has 18 electrons, so that would have a positive charge, when they add that first electron, it actually does not go to 4s. It goes to 3D. So this electron actually gets added first if you're actually thinking about building. But I don't want to confuse you too much. In this video, we're just thinking about the electron configuration, and for that, Aufbau can be very useful. Now, for electron configuration purposes, 3D, you then go to 4p, and then you then go to 5s, and that's why you might see this type of a diagram once again in your traditional first-year chemistry books. So the big takeaway here is the Aufbau principle that you'll learn, this type of diagram, it's useful for electron configuration. And it might be useful to think about it as you're building these atoms electron by electron. But if you really want the precise, accurate truth once you get beyond calcium, it gets a little bit more complicated. Now, one other thing that I want you to appreciate based on what we just learned is patterns in the periodic table of elements. So for which elements are we building out our S subshell? Well, you could see that for all of these elements right over here, these first two columns, we're building out our S subshell. Now, it looks like something is missing there. Is there something else that builds out our S subshell? Well, from that point of view, we could actually think of helium as being right over here, because helium, we're building out that 1s subshell. And because of that, all of these elements right over here, we say that they are in the S block. Now, which elements are building out their p subshells? Well, all of these elements right over here are building out their p subshells, or have it fully built out. And because of that, all of these elements, we call these the p block. And these elements in the middle right over here, scandium is one of them, they are called the d block. Now, one reason why folks might have called the D block is if you really imagine the Aufbau principle as building up atoms, it might be tempting to say, oh, well, we're building in the fourth row here, we're building the 3D subshell, or in the fifth row here, we're building the 4D subshell. Now, we now know that that actually isn't true, but from electron configuration point of view, it can appear that way. And so that's why it is called the D block. And I will leave you there.